All right, so this presentation was done by Kelton, Jordy, and Mason, and we chose the buoyancy problem. For the problem, when an object is submerged in a fluid like water or air, it undergoes a force arising from the pressure exerted by the displaced fluid. This force is termed the buoyant force. For our problem, we need to develop a conceptual framework for this force and apply it to everyday occurrences, such as understanding why certain objects sink while others float. This model also provides insight into the mechanisms behind the ascent, suspension, or descent of items like balloons in the air. And so for us to make an appropriate model, we want to ask some questions and answer some questions about what could affect the object's ability to sink or float. The first question is, what is a fluid? A fluid is a substance that flows and has no fixed shape. It includes liquid and gases. Fluids can exert pressure perpendicularly to any surfaces they contact and can flow and change shape when subjected to an external force. Then there's gravity. Gravity is a force of attraction between two masses. It is responsible for pulling objects with mass towards each other. On Earth, gravity gives weight to physical objects and is what keeps everything anchored to the planet's surface. The strength of gravity depends on the masses of the object and distance between them. Buoyancy is the upward force exerted by a fluid, liquid, or gas on an object placed in it. This force opposes the weight of the object and allows it to float. Buoyancy is governed by Archimedes' principle, which states that the buoyant force of an object is equal to that of the weight of fluid it displaces. Some assumptions that we are making for our model is we are assuming that, once again, Archimedes' principle applies, stating that the object submerged in a fluid experiences an upward buoyant force equal to that to the weight of the fluid it displaces. And then we are also assuming that this is going to be a uniform fluid, which is assuming that the fluid, whether it is water or air, has uniform properties such as density and pressure throughout the region of interest. And then we have the steady state. Consider the problem is a steady state, assuming that the fluid and the object have reached equilibrium and there's no further acceleration. And then we are also assuming that we are dealing with the ideal gas law. And if we are dealing with air, you might assume that it behaves as an ideal gas according to the ideal gas law. In fluid dynamics, you might also neglect turbulence. Turbulence effects unless specifically addressed in the problem, which we are not addressing.
Before we talk about what buoyancy force is, let's compare the following two models. Model 1 is a block placed on the ground, whereas Model 2 is a block submerged in a water tank. This raises the question, which block would be easier to lift up? If we create a force body diagram for Model 1 on the block, the tension force T is the force required to lift it off the ground and overcome gravitational force W for weight. However, for Model 2, the amount of water that has been displaced by the block is pushing back in order to spread out uniformly in the tank. Thus, the forces in this scenario are the gravitational force pulling the block down, the tension force, and the water's force pushing the block from underneath. Think of this force as a restoring force that the water exerts to return to equilibrium, where equilibrium is a balanced consistency throughout the medium. We refer to this force as buoyancy. In models like these, buoyancy is always oriented up and out of the medium, or opposite to gravitational force. The deeper the block is in the water, the higher the pressure. Because pressure is stronger under the block than on top of the block, the buoyancy force pushes upward where there is less pressure. As well, a medium of higher density will provide a greater buoyancy force. Thus, Model 2 will have a significantly greater buoyancy force compared to Model 1. As a result, less tension from your hand is required, making the block in Model 2 feel lighter. Now we will be representing the forces numerically to show what factors affect buoyancy. From this diagram shown, for simplicity, let's assume that our cylindrical object is uniformly shaped, so that the surface area on top equals the bottom. Thus, there are two forces from the water that are applied to the object: the pressure of water from above and the pressure of the water from below, F2. There are as well horizontal forces that similarly act on the sides of the object, but these left and right forces cancel out. As addressed in the last slide, because pressure becomes greater the deeper in water you go, F2 will be larger than F1. The difference between these two forces will give us buoyancy, as represented here. Because buoyancy is largely dependent on pressure, we can start by using the equation pressure equals force over area. We can isolate F and substitute this expression to give us a foundation for our buoyancy equation, P times A2 minus P times A1. However, we can further build off from this. Since we said that buoyancy is also largely dependent on the weight of the medium, since the force exerted by the fluid is essentially the weight of the fluid, we can say that this equals the force of gravity, m times g, or mass times gravity. From the density equation, we know that mass can be replaced with density times volume, and volume can be further substituted for the surface area times its height, which gives us 3 dimensions for our object. With the areas canceling out, we have an expression for pressure. Substituting this will give us a complete equation for the buoyancy force. The density of the fluid, represented by Greek letter rho, times gravity, times the area of the object, times the height of the object. The height is the difference between h2, which is measured from the water surface to the bottom of the object, and height 1, which is from the water surface to the top of the object. To highlight again, this equation assumes that the object is uniformly shaped, meaning that the surface area is the same on top as it is on the bottom. Thus, we can simplify the equation and combine the areas A1 and A2, giving us this final equation below. Slide 4. This final equation thus tells us that increasing any of these variables will in fact increase the effect of buoyancy. Increasing density or gravity is like increasing the strength of the hand pushing up against the object from underneath, whereas increasing area is like increasing a platform that more people can push up against. If we assume that the object is fully suspended under a fluid F, the amount of volume the object occupies should be equal to the volume of fluid displaced by the object, such as water. Based on our density equation, we can say that the volume of fluid displaced times the fluid's density is equal to the fluid's mass times gravity. This is equal to the gravitational force W, the weight of the fluid. Our equation thus says that the force of buoyancy equals the weight of the fluid displaced by the object. This is a very powerful representation, as it proves that an object heavier than the same volume of water it displaces will sink, whereas an object lighter than the displaced water will float due to a stronger force of buoyancy. Referencing Newton's third law of motion, if the object's weight is equal to the water's weight, then the object will sit suspended, neither sinking nor rising. The following slide describes 2 real-world examples that fundamentally relate to buoyancy. Hot air balloons rise because the buoyancy force is greater than the weight of the balloon and the basket combined. Don't forget that the concept of buoyancy can still apply to air, as air is just a very light medium. Though the balloon and the basket are both objectively heavier than air, they still float because hot air collects in the balloon. Hot air is less dense than the surrounding cold air. As well, the balloon occupies such a large volume of hot air that the object's overall density is lighter than the medium around it. Thus, buoyancy lifts the balloon higher up. Another example of buoyancy is a clay ball being set in water. Clay itself is undeniably denser than water. Thus, rolling the clay into a ball will cause it to sink, as the ball is denser than the water it disperses. However, if you can mold it into a boat, you could potentially have it float. This is because the opening you have created inside the boat is full with air, which is lighter compared to water. This new total volume is overall less dense, and the surface area over which the buoyant force acts is larger. Thus, for the area of the clay boat that is immersed in the water, the weight is equal to the weight of water displaced, which is why it does not sink.
When put in the equation, buoyant force is equal to PVG. On this slide, it shows how the calculations would work if we were provided the necessary information to calculate the problem. If we know all the values for the variables included, then the solving process is rather simple. Using the equation buoyant force is equal to P times V times G, we simply would just multiply the density of the fluid the object is in, the volume of the fluid displaced by the object, and gravity all together. This would give us the resulting buoyant force acting on the object. On the right-hand side of the slide, these excerpts show that if the weight of an object is greater than its buoyancy, then it will sink, and if the weight is less than the buoyancy, then it will then in turn float. In the middle of the slide here, we put numbers into the equation with the buoyant force equaling an object, the density of the fluid, which was 1,000 kilograms divided by meters cubed, times the volume of the fluid displaced, which was 0.002 meters cubed, and then once times gravity, which would then give us the resulting buoyant force as a number. For this sense-making slide, we'll be talking about buoyant force as it opposes the weight of an object, and then the equation that we use to solve for the buoyant force and how it is similar to previous equations we have learned in Physics 212 this term. So the buoyant force is the upward force exerted by a fluid that opposes the weight of a partially or fully immersed object. For example, in a column of fluid, pressure increases with depth as a result of the weight of the overlying fluid. This means that the pressure at the bottom of the immersed object is greater than the pressure at the top of the object. The difference in pressure is what creates an upward force on the object, which is known as the buoyant force. In our equation that we use to solve for the buoyant force equals PV times G, we see variables in this equation that we are already familiar with in gravity and force. Along with this equation, we are also learning two variables that we have not seen before and that we can help add to our physics model to help us understand and solve this problem, with V being the volume of a displaced fluid by an object in water, and P being the density of the fluid displaced. The equation itself is nothing complicated, as it is just multiplying across, or if we need to solve for missing variables, we can do some simple division to set the equation equal to what we need to know. Reflection. Using the equation buoyant force equals PV times G, which is the equation for buoyant force as previously stated, we are able to understand the relationship between buoyant force and previous equations we have seen based on the variables used. From previous physics models, we know about volume and gravity. The only variable that is new to our model is fluid density. Since the equation is multiplying these variables, it does not require us to learn any new concepts or physics principles to help solve this equation. Another thing that was learned when solving for this, or that we could apply to our physics model, was the Archimedes principle. Archimedes' principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether full or partial, is equal to the weight of the fluid that the body displaces. Using Archimedes' principle in the math we have learned, we can help explain why some objects sink and why some objects float. Objects that sink in water are denser than the fluid that they are immersed in, which means that the weight of the object is greater than the buoyant force, so the object sinks. And then vice versa. Objects that float are less dense than the fluid they are immersed in, which means that the buoyant force is greater than the weight of the object, causing it to float. When talking about balloons and how they work, since they are not in a liquid and rather just rise and fall through the air based on gas and air, balloons are filled with a gas such as helium, which is less dense than air, which means that the buoyant force on the balloon is greater than the weight of the balloon, so the balloon will rise. If the balloon is released, it will eventually fall to the ground as the gas inside the balloon starts to leak out, causing the air to become more dense than the gas. Reasons why ships float is because the buoyant force of the water is greater than the weight of the ship. And as previously stated, balloons rise because the helium inside them is less dense than the air around them. And then here's also a fun fact about fish regarding buoyancy. Fish can swim without sinking because they have air bladders that they can adjust to control their buoyancy, which helps them rise and fall through the water. And then submarines as well have buoyancy tanks that they can adjust that also help them rise and fall through the water. Thank you for listening to our presentation.